Hey everybody, welcome back. Today we're going to finish up our fourth unit, Contextual Applications of Differentiation. And we're talking about topic 4.7, which is using LHopitals or LHopitals Rule for determining limits of indeterminate functions. Okay? So in this section, we're going to go back to our roots here, back to where we started our year off with limits. Okay? Back in our first unit, we did a couple examples like the following two. Hopefully you remember how we did these. Okay? With all limits, the first thing you want to attempt is to put the C value, so in this case the C value is 2, in this case the C value is infinity, directly in for x and see if you can get a value back. Sometimes that works right away, sometimes it doesn't. In both of the cases above, it's simply not going to give us numeric value. Okay, if we tried that, if we put 2 into the first limit, we would get 0 in the numerator and 0 in the denominator, so 0 over 0. If we put infinity into the second one, we would get negative infinity in the numerator and infinity in the denominator. Okay, these are called indeterminate forms. Basically, they aren't numbers. Okay? There are a variety of these. You can see here, we got 5 like this and another 6 or 7 like that. All these forms are called indeterminate forms. Okay? And actually finding limits using these forms was added to the AP Calculus curriculum about 4 years ago, back in 2017. And for what we're going to do right now in this class, we're just going to focus on these forms, okay? We're not going to focus on these. If you end up taking a Calculus 2 in your future, you'll talk about those later on. Now, going back to those first two problems, we could factor, cancel, and then try again. Okay, and that would be a relatively easy thing to do for these two problems. But that's not always the case. Consider these two limit problems right here. There's no factoring available in the numerator of the first one or the second one. So we cannot solve these by using factoring or any other algebraic technique that we know of for that matter. Yet, their limits actually do exist. As x approaches 0, look, we have an answer for that first one. As x approaches infinity, we have an answer for that one as well. So the question is, how do we find them? And that's where our good friend here, L'Hopital or LHopitals, comes into play. Okay? Some textbooks spell it with an S. Some textbooks spell it without an S. Both are accepted. I generally say LHopitals Rule, but sometimes it looks like LHopitals Rule or LHopitals, which is not the correct pronunciation, but I do hear that being said often. But L'Hopital is what I will be calling it throughout this video. Okay? So L'Hopital's rule says if we have one of the following two cases, limit as x approaches c equals f of x over g of x, where both limit of the numerator equals 0 and limit of denominator equals 0, or the limit of numerator is one of the infinities and denominator limit is also one of the infinities for any real number c, or for c having the value of infinity or negative infinity, then the limit of f over g is the same as a limit as f prime over g prime. Let's take a look at how that works. So here we have our first example. It says limit as x approaches 2 of this beautiful function, rational function here. As always, the first thing you want to attempt is to simply put the c value in and see what we get back here. So that would be 12 minus 14 plus 2, which is 0. And 2 minus 2 is obviously 0. So we get 0 over 0. If you go back to our limits chapter, if you remember correctly, that actually tells us the limit does exist. Now we just got to do some work to find it. You could try to factor and cancel this here, but L'Hopital's rule tells us all we got to do is take the derivative of the numerator and the denominator separately. So we're not using quotient rule here. Okay, that's not the rule. We're not trying to take the derivative of this whole thing. We're taking the derivative of the numerator and denominator separately. And then we could try again. And our limit is 5. And that's how LHopitals Rule works. Let's take a look at a couple more examples. So B, if we put negative 3 in here, we would get 0 in the numerator. And 0 in the denominator. So we know LHopitals Rule will apply. Derivative of the numerator is 1. The derivative of the denominator, we get 1/2 x squared minus 5 to the negative 1/2 times 2x minus 0. So you don't have to write that last part there. All right, if we want to simplify that a little bit, the x squared minus 5 to the negative 1/2 comes to the numerator here. I'm going to write it as a root instead of a exponent. And the denominator, the 1/2 and the 2 cancel, so we're just left with x. And now, if we put negative 3 in again, we get our limit is negative 2/3. Part C, this is a crazy looking rational expression here. So we get negative 2 cubed plus 2 squared, negative 2 squared, minus 8 times negative 2, minus 12, that would be 0. And denominator, we get negative 8 plus 32 minus 40 plus 16, which would also be 0. So LHopitals Rule applies. Take the derivative of the numerator and the derivative of the denominator. All right, and let's try again here. So we put negative 2 into the numerator. We get 12 minus 4 minus 8, that's 0. And then the denominator, we would get 12 minus 32 plus 20. And that's also 0. So you know what that means? That means we can do LHopitals Rule again. All right, let's try this one more time now. Now we get negative 12 plus 2 over negative 12 plus 16. All right, LHopitals Rule says the limit of this function as x approaches negative 2, this function as x approaches negative 2, and this function as x approaches negative 2 will all be negative 5 over 2. All right, part D. If we put 1 in here, we will get 5 minus 4 minus 1, that's 0. 10 minus 1 minus 9, that's also 0. So LHopitals Rule will apply. If we put 1 in, we would get 20 minus 8 over negative 1 minus 18, which is 12 over negative 19, or negative 12 19ths. All right, quick note here. It's important that you never actually write a limit equals 0 over 0 or infinity over infinity. Those things don't exist. They're indeterminate forms. They don't work, so we really should never set them equal to it. So you can see here, that's why I'm just writing the limits separately here. I'm just writing the numerator and denominator separately for each one. I'm not setting it equal to our limit, because 0 over 0 is not a number. Infinity over infinity is not a number, so we can't set that equal to our limit. All right, so here are 4 problems that you should try on your own. Feel free to pause the video at this point. Try these 4 problems, and then when you're done, unpause the video to check your work and answers. All right, for A, we should have got 0. Again, feel free to pause the video on each of these if you want to check them out in more detail. B, you got negative 1 over E. C, negative 5/3. Had to apply LHopitals Rule twice there. And D, you got 0. And LHopitals Rule applies twice there as well. So, beyond those type of problems, we always might see problems with graphs or tables. Let's take a look at problem A here. The graph of f is shown below. Find the limit as x approaches 3 of f of x over x squared minus 9. All right, so let's take a look here. The limit as x approaches 3, so f of 3 would be 0. And then 3 squared minus 9 would be 0. So this is 0 over 0. So that means LHopitals Rule applies. We can take the limit as x approaches 3 of f prime of x over 2x. So f prime of 3 is the slope here at 3. Let's say we're going down 2, right 1, down 2, right 1. So that would be negative 2. And then 2 times 3 would be 6. So negative 2 over 6, or negative 1/3. The functions f and g are differentiable for all x. Use the following table to help find the limit. All right, so we have limit as x approaches 2. If we were to put 2 in, so f of 2 minus 4 will be 4 minus 4, which is 0. And then g of 2 times 2 squared will be 0 times 4, which is 0. So 0 over 0, which means LHopitals Rule will apply to this problem. So limit as x approaches 2 of f prime of x minus 0 over g of x times 2x plus x squared times g prime of x. You got to use the product rule for that denominator's derivative there. Now we can put 2 in again. F prime of 2 is negative 2. And then g of 2 times 2 times 2 plus 2 squared times g prime of 2. All right, g of 2 is 0, so this whole thing cancels out here. And we're left with 4 times g prime of 2, which is 3, so 12. So our answer here is going to be negative 2 over 12, or negative 1/6. Okay, last one here. Let f be a differentiable function, a function defined by e the x cosine x. Let g be a differentiable function, such that g of pi over 2 is 0. The graph of g prime, the derivative of g, is shown below. Find the value of the limit as x approaches pi over 2 of f over g, or a state that does not exist, and justify your answer. So this is a problem from 2018 on the AP exam, part D, on number 5. Okay, so the first thing we want to do is put pi over 2 in here. F of pi over 2, so that would be e to the pi over 2 times cosine pi over 2. So e to the pi over 2 cosine pi over 2. Cosine pi over 2 is, of course, 0, so that would be 0. G of x, it tells us g of pi over 2 is 0. So g of pi over 2 is 0. So we get 0 over 0, which means the limit exists, right? So now we can say, by LHopitals rule, the limit as x approaches pi over 2 of f prime of x over g prime of x. So f prime of x would be e to the x times negative sine x plus e to the x cosine x. So f prime of pi over 2 would be negative e to the pi over 2 times 1 plus e to the pi over 2 times 0. So that would just be negative e to the pi over 2. And then for g prime, this is g prime, right? So g prime of pi over 2 is just this point right here. So it would be 2. So our answer here would be negative e to the pi over 2 over 2. And that's what our answer would be to the original problem as well. Limit as x approaches pi over 2 of f over g would be negative e to the pi over 2 over 2. Okay, that will do it for this section and for this chapter in general. Thanks again for tuning in today, everybody.